So we are going to talk about interferences and the complex processes that goes beyond. So to observe interferences, the easiest means is to take a quite thin and transparent surface, such as a film of oil covering some water, or the outer surface of the wing of some insects. The document is presenting us the phenomenon by taking the example of soap bubbles. Indeed, soap bubbles fill all the criteria to observe interferences, so they have a thin and transparent surface. And it's true that when you look at soap bubbles, you see a very large spectrum of colors: white, red, purple, blue light, while in fact only white light is lighting up the bubble. And this display of color is due to interferences. So the document with the graphic explains us how we got such a display of color. For interferences, you need two similar waves, and by similar I mean that they must have the same frequency, and that they must be produced at the same time. And it's impossible to observe interferences with two different sources, because it's impossible to create two exact same waves with the same frequency and the same phase. So you need to take one source but two ways to observe interferences, and that's here that the thin and transparent surface that we have talked about plays a role. So we have the surface of soap bubble, we have an incident light that arrives to the outer part of the surface. So when it arrives at the outer surface, two things happen. First, a part of this light is reflected, and it will be our first ray for the interferences, because we need two rays. And another part of the light will be refracted and go through the surface toward the inner part. And when the light will arrive at the inner part, the same two things will happen. One part of the light will be refracted and go inside the bubble, but we don't have to take care about this. And another part of the light will be reflected, and so it will go back to the inner surface of the bubble, of the surface of the bubble, where again we will have the two phenomena. One part of the light will be reflected and go back to the inner part of the bubble, and another part, which is the one that is interested in, is the light that will be refracted. This refracted light will get out of the bubble, and so we will have from one source two ways that get out of the bubble, and this is these two ways that will create interferences. But to have interferences, you need the two light passes to cross each other, and when the two ways that get out of the bubble, they are parallel. So we can see in the document that they seem parallel, and so that's something that we can prove due to the formula of Descartes. So we are gonna represent the surface. So this is the inner part of the bubble, the outer part of the surface, and the inner part. And so this is our incident light. They will go like this, and here one part will be reflected. That will be our first ray. So, and here we have alpha angle. Let's call it alpha. So here it will be the same angle, because when the light is reflected, it's reflected with the same angle. So another part will be refracted, as we say, then reflected, then here it will be refracted. And so here we don't know this angle, which is the same as this one. Let's call it x and x2, and this one will be x1. So so we can find this x2. So we know with the Descartes formula that n1 which is an index of refraction of the first environment, multiplied by sin of alpha is equal to n2, which is the index of refraction of the second environment. So times sin. So we are going to x2. So we can write this: sin x2 is equal to n1 divided by n2 times sin alpha. So now we want to this angle that is interesting us. So with the same formula, we can say that n2 x times sin x2, which is this angle, is equal to n1 times sin x1, the angle that we are interested about in. So we can write this: sin x1 is equal to n2 divided by n1 times sin x2. And so sin x2, we say that it was equal to this, and when we can write so times x1 divided by n2, that sin alpha. So when we can write sin x1 equal sin alpha. So we have alpha equal to x1, or alpha equal to p minus x1, but we are not interesting. It's not very interesting. So now we have proved that these rays are parallel. So the interferences, so the moment when the light passes will cross each other, will happen in the eye. And so when interferences will happen in the eye, the distance that each of the rays will have the distance of the way you have traveled will be different for the two rays between the emission and the moment the path crosses. So one way will have due let's call a distance d, and the other way will have due a distance d plus something, and let's call this something y. And so if y is equal to k time the wavelengths with k being a whole number, the wavefronts will be with what we call in phase, which means that the two waves will have the max will reach the maximum of intensity and the minimum of intensity at the same time. So when the two lights will cross, to find the intensity of the new light that will be created, you have to add the two intensity, and so because they get the max at the same time and the minimum at the same time, we will have a light with more important intensity, so we will have light. But if the y is equal to k time the wavelength plus 1 divided by 2 times the wavelength, the two waves will be 180 degrees out of phase. So when one will reach its minimum of intensity, the other one will reach its max of intensity. So when we will add up, we will have no intensity at all, so no light. And that's how interference exists. So in our eyes, when we look at a soap bubble, a lot of interference takes place. And so it depends on which part of the bubbles you are looking at, and it depends of the color, because every color will have a different refraction. So in yours we'll have tons and tons of interferences, and that's why we have such a display of color by looking at soap bubble, and that's why the document is telling us. And this is just one reflection, interferences. This is just some properties of wave, but there are many more that, for example, the electromagnetic waves travel at a constant speed, and without that, we won't be able to have a Doppler effect, and the Doppler effect is a difference between the frequency of emission and the frequency of reception when two objects move. And without a constant speed, we won't be able to use this property. So we have also, let's say, microwaves, which are a type of electromagnetic waves that can make the matter move. And we know that that the more the matter moves, the more important the heat is. So that's just examples of the many properties the waves are and their applications.